Welcome to Maths with EJD. We are still talking about differential equations, and in this video, we are considering applications of first order ordinary differential equations. I mean, I've talked about a few of them in the course of the video so far, but I mean, most importantly, we have seen different uh, types of first order, okay, first order ODEs, right? So first of all, um, we've seen separable. We've seen separable equations, that's separable first order differential equations. Okay, we've also seen linear, we've seen linear equations. So linear equations that involve the use of integrating factor, we've seen that also. So when you see an ordinary differential equation of first order, right? The first thing you want to check is it, can you separate the variables? Okay. So after separable equations, we've seen the Bernoulli equation. Bernoulli equation. Bernoulli equation is non-linear, but with some transformation, you can make it linear and then use the integrating factor to solve it. Okay. Then in the last video, we saw exactness. We saw exact equations. So we saw exact equations. And for exact equations, you need to verify the exactness and then solve and then find a potential function that satisfies the equation. Okay. So we've seen all this so far. So what we are going to be considering here is applications of all of this because differential equations are extremely applicable in real life situations. Okay. But first, can we just have an overview about the topic itself before we start looking at some specific applications? So first order ordinary differential equations model many real world phenomena, many real world phenomena, phenomena. Okay. These applications, these applications span various fields such as physics, biology, economics, and engineering. Okay, so let's look at some specific situations, some specific applications. First of all, we have it in population growth. We've seen an example of this previously, population growth, and it's usually exponential growth, right? Exponential growth. Okay, so here, a classic example of a first order ODE is modeling the growth of a population under ideal conditions. That is, no limits on resources. So the rate of growth is proportional to the current population size, leading to the equation that we have dp, the PDT is equal to KP. We've seen this a couple of times. So in this situation now, you have P of T. P of T is the population, population at time T. So this is a very idealistic equation in the sense that we assume no limit on resources. It means there is unlimited space, there's unlimited food for growth. So that's why it is not realistic because in reality, there are actually restrictions, there are limitations, and that's what can lead us to other types of population models like logistic growth, which saturates at some point because of carrying capacity and things like that. Then here, constant, K is a constant rate of growth. So that is of course another idealistic thing because growth rates can be time dependent. Okay, but here we just assume that. So interestingly, the solution to this problem. So the solution is something like this. You have solution. If you solve that equation, you get P of T equals P naught of e raised power KT. That's what you get when you solve. Of course, this is easily separable. like we saw before. So here now you see that P naught is the initial population size. So P naught is the initial population size. Okay. Then this is possible, for example, if a population of bacteria doubles every hour. In that case now, if a population of bacteria doubles every hour, we are assuming that K is equal to ln 2. Okay. So, and there are initially 100 bacteria. That's if you say P naught is equal to 100 when we started out. So the population at time T is now going to be something like this. P of T equals 100 times 2 raised to power T, basically. So that's a specific situation like that. Okay. So that's population growth, a very popular way to for that, right? So we have also radioactive decay. That it is just like the opposite of exponential decay, exponential growth rather. So the only difference here is that the constant is declining. So radioactive decay is governed by first order ODE, where the rate of decay of a substance is proportional to the amount of the substance present. This is described by the N, the T, okay, equals minus lambda N, right? So here N of T is the quantity, N of T is the quantity of the substance, the quantity of the substance at time T. I think, I mean, we've come across this in physics textbooks before now. Then lambda is the decay constant, the decay constant, which is a positive value, but the negative in front of it ensures that it decays. So it's a positive value. So here, the solution to this equation now, to this particular equation we mean, is just like the population thing. So N of T equals N naught e raised to power minus lambda T. Okay. So that's the solution to that because it's easily separable. All right. So N naught here now is the initial quantity of radioactive substance. So that's initial quantity. So if you want to look at an idea, a specific situation, for example, if a sample of a radioactive isotope decays at rate lambda equals 0.1 per year, okay, and then initial number of substance is 100 grams, and then if you give it 5 years, if T is 5 years, right? So all of this is going to lead to N of 5, okay, which is equal to 100 e raised power minus 0.0 lambda, right? That's 0.1 times 0.5. So that's basically 0.5, okay? And that is approximately 60.65 grams at the 5th year. Okay, so that's one other instance of this. Then we go for number 3 application of first order. So number 3 would be Newton's law of cooling. Newton's law of cooling. So it's more like bringing a substance to the ambient temperature of its environment. So this law describes how the temperature of an object changes over time when placed in an environment with a different temperature. So the rate of change of the object's temperature is proportional to the difference between its temperature and the ambient temperature, leading to the equation dt. So the rate of change of temperature of the object that has been brought into an environment with a different temperature will now be minus K into T minus T ambient. So T ambient is the temperature of the environment, while T itself, the first T, is the temperature of the object. Okay. So here now we have T of T to be the temperature. T of T is the temperature of the object at time T. Okay. Then T ambient, like I said already, T ambient is the constant ambient temperature. Okay. And of course, K is a constant. K is a constant. So if you solve that problem, if you solve that particular problem, you have the solution, right? The solution is T of T, which is equal to T ambient. The solution is T ambient, okay, plus T naught minus T ambient multiplied by e raised power minus KT, because the temperature is probably, it's actually cooling, right? So the temperature is being brought down, so to speak. All right. So here, as usual, T naught is the initial temperature, the initial temperature. Okay. Um, so if we have a particular instance, right? If we say if an object is an initial temperature, so let's say T naught is 90 degrees centigrade, is placed in a room where the temperature, the ambient temperature is now 20 degrees centigrade, and the cooling constant, K, is 0.05. This is the cooling constant, K. So if the cooling constant is 0.05, so the temperature after 10 minutes, if we give it 10 minutes, right? So the temperature would be T of 10. That'll be T of 10 equals 20, the ambient temperature, plus 90 minus 20 e raised power minus 0.05 times 10. That's 0.5. That'll be 0.5 there. And this is approximately 53.8 degrees centigrade. So after 10 minutes, the object would have cooled down from 90 degrees centigrade to 53.8 degrees centigrade. Okay, that's the fourth one. I mean, that's the third one. The fourth one is charging. Okay, charging slash discharging, charging or discharging of a capacitor. Charging or discharging of a capacitor for an RC circuit. Okay. So in an electric circuit containing a resistor and capacitor, so RC circuit has resistor capacitor circuit, the voltage across the capacitor during charging or discharging follows the first order ODE. So for discharging, the equation will be dV dt equals minus V over RC. Okay. So that's what we get for that. Here now we have V of t. V of t is the voltage, across the capacitor at time t. Then you have R. R is the resistance. And then C is the capacitance. C is the capacitance. So if you solve that problem, right? If you solve that problem, you're going to get the solution to that problem. The way it looks, it's I think it's variable separable, because I mean you'll be given those other values. So it's variable separable, so you can just separate and solve. So solution is V of t equals V naught e raised power minus t all over RC, like this. So that's the solution when you solve that problem. So V naught here is the initial voltage. Initial voltage. So if we have an example where we have a capacitor has V naught to be 10 volts. Okay. Then we have the resistance to be 5 ohms. The capacitance is 2F and discharges the voltage at T. Okay. And then we now have time, like after 1 second, what will be the voltage, right? Starting from 10 volts. In just 1 second, it will be having V of 1 to be equal to 10 raised to the power E minus 1 all over 10, because that will be R times C. That will be this R times this C now. Okay, so 1 over 10, and that is approximately 7.39 volts in that situation. Okay, so that's what we get from that scenario. Okay, so we go for the next one. We have heat transfer in a rod. That's another real life application. Heat transfer, heat transfer in a rod. Okay, that's another application. In the case of heat conduction in a rod, the temperature at a point on the rod may change over time based on heat flow. This is modeled by, so here we are talking about space and time. So that becomes dt equals alpha d squared t dx squared. So x is space, t is time. So this is, in fact, this should be partial differential equation, right? Um, so I think it's better to write it as a partial thing, though we have not really dealt with partial differential equations under this topic, but I've dealt with it under numerical analysis. Partial t equals alpha partial squared t partial x squared. So space and time. So here we say that t is a function of x and t. So this is the temperature, is the temperature at position x, the temperature at position x, and time t. So space and time are involved here. And then we have alpha. Alpha is the thermal, alpha is the thermal. Oh, actually, this is a second order ODE, right? But under specific boundary conditions, it can be simplified. Okay, good. I think that's the essence of this. So alpha is the thermal diffusivity constant. Diffusivity constant. Okay. So the caveat here is that this is actually a second order ordinary differential equation. In fact, it is not second order, it's actually a second order partial differential equation for sure. But under specific boundary conditions, it can be simplified to a first order ODE for the average temperature. Okay, I think this point is really important. Okay. So this is not a first order thing like we are simply really saying, but then this is a second order. It's a second order ordinary differential. In fact, it's a second order partial differential equation for sure, but under specific, under specific boundary conditions, under specific boundary conditions, it can be simplified. It can be simplified to a first order ODE for the average temperature. Okay, for the average temperature. For instance, if we use a method like shooting method, right, we can make it into a system of first order equations, and then we have that. So this last example is not particularly a first order example, but then it can be transformed into that using under certain situation. All right, so that's the end of this video talking about the application. So you have seen some real life applications of first order ordinary differential equations. All right. So let me know in the comment section how helpful these videos are for you. And if you have subscribed to this channel, thank you so much for that. If you have not done that already, you want to do that right away, because you have a lot still coming as far as differential equations are concerned. This is just the end of first order differential equations. So we're going to talk about second order differential equations starting from the next video. And then we still have higher order, we have system of equations and all of that. So you don't want to miss out on any of this. So be sure to subscribe and hit the notification bell so you can always get alerted each time a new video is released. Let me also know in the comment if there's a topic you'd like me to teach or a problem you'd like me to solve, right? And like and share so that more people can have access to this great content. Till I come your way again, keep doing maths right. Bye.